Hello everyone, my name is Kevin No,
My name is Brandon Nguyen.
and we will be presenting our final project for CCS 440, known as the FPU, or Fundamental Processing Unit. So first off, we want to go over just a quick overview of our presentation. First, we'll introduce the FPU. Second, we'll briefly go over processor specifications. Third, we'll go into detail on our enhancements we've made. Fourth, we'll talk about future enhancements, and fifth, we'll finish up the presentation with some Q&A.
Kevin, can you move the mouse pointer? Thank you. All right. So just a quick introduction. We chose FPU, stands for Fundamental Processing Unit. So we wanted to create a processor that is very easy to use and is really user friendly. The instructions that we implemented kind of help out the user to work with the software or hardware interface. For example, for a push and a pop, instead of worrying about loading the word or storing the word and then either post-incrementing or pre-decrementing, it's just one instruction and it automatically does it for them, so they don't have to worry about that. And then our FPU, it has three components. It has the instruction unit, the MIPS control unit, and then the intermediate path.
So jumping into our processor specifications. The FPU has a 32-bit instruction word format and uses three instruction types: the R type, I type, and J type. Two data types, unsigned and signed 32-bit integer. It uses the Harvard memory architecture, which basically separates basically where the data and instruction memories are separated, and it uses big endian format, which is where the most significant byte is saved first, and the least significant byte is saved last. Here's the register file as part of our register. Register set. Some of the highlights of the register file are register 0, which has a default value of 0. It's a read-only register, which means it will never be changed. Let's see, register 29 is our stack pointer, which points to the top of the stack, and register 31 is the return address, which is essential to our jump and leaf instruction, as it saves the address.
Next, we're going to go into addressing modes. So we have three addressing modes. We have immediate, which is either 16-bit or 26-bit for our add immediates, or the 26-bit which would be for our jumps. And then we have register direct and then base index.
Which register direct? Which one's that? What do you use that for?
Register direct, it's like a register where you do register. For example, an add, you have the two registers as operands, and then you store it to another register.
Got it, thanks.
So we're just going to go over an immediate example. So up here, this is our I-type format. We have our 6-bit opcode, then we have a 5-bit RS, and then a 5-bit RT, and then followed by an immediate offset, which is 16 bits. So right now we're at the example is going to be an add immediate example. We're using register 4 as the RT, register 5 as RS, and then a negative 16 base 10 as the 16-bit immediate. So essentially, the register 5 contents are going to be just 00D, and the immediate value is negative 16. So then we convert that to base 16. As you can see, the 16th bit right here is going to be sign extended to keep the negative sign when we're adding the two values. And when we add to the two values, it becomes negative, FFFFD. So this is 13, and then this is negative 16, and then that result is negative 3. Okay. And move on to the next one. And then,
I got this. So this is an example of the register direct addressing mode. So you can see here that we're using a R type instruction. In our example specifically, we're using the add instruction, where we add register 7 with register 8 and storing it into register 6. Here's the RTL for it. And so here basically we just add A4, which is in R7, with register 8, and we get E9 as our result down here.
For base index, it's generally used for load word, store words. So essentially, it's going to be an I type again, and so for the load word, it's the register 4 is going to be our destination register. The 4 in front of the parentheses is going to be the offset, and it's generally a base 10 offset, and then the whatever is inside the parentheses is going to be another register, and that's your base register. So what happens is you take your base register and you add it with the offset, which is in front, and then based off of that offset, you access memory for at least a load word. You access memory, and then you take whatever's in that memory location, and you bring it and store it into register 4. So we have the top level schematic here. We just wanted to highlight the CPU itself. So the CPU has 3 main components. It's the MCU, the IU, and the IDP. And the outside modules are going to be our I/O module and our data module. Essentially, the MCU is going to be has all of the output or control words going into the IU, IDP, and specifically for the I/O module, there is a interrupt acknowledge from the MCU going to the I/O module, and the I/O module actually sends out an interrupt to the MCU when it's ready, or when it has data from the input output. Would you like to add anything to this?
No, I just wanted to highlight, these are all the outputs out of the MCU into the IU and the IDP blocks. And also the MCU gets these inputs here. I believe this is an interrupt request, our flags, and then another, this is the flags in wire. And yeah.
And also, we have our instruction unit kind of zoomed in on the next page. Just real quick, for the PC mux, all it is PCN, which is coming from the IDP LU out when you do your effective address calculations. Then you have this next wire, which is for jumps. This one's for branches. The PC select, PC load, PC inc, and then the instruction memory control signals, they're all coming from the MCU. And then these outputs, this is the instruction register and the signing send 16. Those are going to the IDP. And we have our IDP. For S address and then T address and D address, those are all coming from ALU or from the IR out, coming as an output from the instruction unit. That's to just break down the instruction format like what we had for I types, R types, J types, and that's how we get the data and figure out the instruction of what we're doing. Next we have just 5 basic registers. DY, if you look in the top level in the first page, DY, before DY has a mux, that mux controls either we're taking in the data memory output or the instruction or the IO output. And depending on if the IO has data coming in, then we select the IO to be into DY, and then vice versa for the data memory. Then we have our high-low registers for multiply divide. We have our ALU out for other basics operations, and then our DN is from DN is from
Oh, DN is from
PC.
PC, I believe, yeah.
Yeah.
DY is the data memory.
Yeah. And yeah, and we can continue. You guys have any questions so far? Just basic MIPS baseline. So then our enhancements for our FPU is going to be push pop, push immediate, add saturated, subtraction saturated, and absolute value. So our push instruction is going to be based off of R type. Essentially the format is going to be push RT. So you just write push, and then you have your the address register where you want to push onto the stack. It updates the PC. So our design does a pre-decrement for push. So then our pop's going to be post increment. So first we decrement the stack pointer, and then we take the contents of RT and store it into memory. For the next slide, we have an example.
Wait, let's go back for a second.
Go
that's an R type? So how come you didn't use our E key for the push? In other words,
So,
you can't change the MIPS architecture. What if the MIPS has that opcode already used?
in the baseline so far, it hasn't been used. It was a
No, not the baseline. So the purpose of having the E key is we don't stomp on anything, because the baseline is just a subset of MIPS. So you can't steal an opcode from R-type that's already used by other MIPS processors.
Yeah, so it was a pretty major oversight on our part. In our next revision, we'll be sure to include the E keys to,
Yeah,
to
okay,
reserve the.
okay.
Yeah.
So going forth, all of your enhanced will have
Right.
like an R-type. Okay,
Yeah,
good,
yeah.
yeah.
Yeah. So for our push example, we have we are gonna push register 12 onto the stack. Our stack pointer currently is gonna be 404, and then these are the memory contents before the push instruction. We first do a pre-deck, so then we take 404 and we subtract 4 from it. So then our new updated SP is gonna be 400. Then since our new SP is 400, our register 12 is 2A10. So the memory after the push is going to be at 400. It updates to 2A10 in the green.
So you guys enhanced your memory module to go beyond 3FF? Because 400 wouldn't work. So that couldn't have been verified unless you changed your memory module.
This is just a, I guess, arbitrary value.
Hypothetical, huh?
Yeah,
Yeah.
Okay, so this was never verified.
We'll further just describe or explain our verification, our actual
Yeah.
verification.
Okay.
Because we have our log file. Yeah, we have our
Yeah.
log file and also the memory module. This is
Okay.
I just use
Just an
arbitrary
example.
numbers.
Got
Yeah,
it.
yeah. So we can go ahead the next one. So our next one we're gonna go to pop. So instead of doing a pre-decrement, we're doing a post-increment for pop. It's the same thing, except now we're taking the memory address from the stack pointer is pointing to, then we store it into the register destination address. Again, we just didn't use an E key. And then we're gonna go to the next slide. So yeah, so for example, we're gonna pop into register 8. So it takes the memory address from the stack pointer, which is 3FC currently, and then we go to 3FC. We see that it's 101. So we take 101 and we're going to store it into register 8. But then we have to make sure we post increment the calculation. So we incremented 3FC to +4, so it's 400. So yeah. Next we have our push immediate. This time it uses an I-type, and what we're going to do is we're just going to do the same thing as a push. We're going to put pre-decrement and then load the immediate into the stack.
You sign extended probably?
Yeah.
Just take the same sign extension.
Yeah, yeah. So we're going to go to the next one. So yeah, first we take the stack pointer, which is 60 right now. So this is the memory before the push immediate. We have a pre-decrement calculation, so it's 60 minus 4, which is 5C. And then we have to convert the 129 from base 10 to base 16. So the conversion is to 81 hex. And then we take the new stack pointer, 5C. We go to that memory location down here, and then we update it with 81, the base 16 calculation.
Mhm.
Put it in there. And then Kevin's going to talk about our memory module, and then also our annotated log file to
Good.
test for verification.
Yeah, so this is where we verified our push and pop instructions. As you can see here, these are just arbitrary values that are loaded into R1, R2. Then we jump into our push instructions here. We push R1 and R2 onto the stack. Then we push our immediate values of 3 and 4 onto the stack. Then we pop all of these four previously pushed values, pop them into 3, 4, 5, and 6. Then we do just a couple of checks. We check 1 against 6, 2 against 5, and if those fail, we jump to these error instructions. If not, we'll clear R14 and to indicate all instructions have been passed. So here's our log file. You can see here, R1 and R2, again, arbitrary values are loaded into R1 and R2, and then we push those values onto the stack. Here, you can see here, 3FC is our initial stack pointer, and then we decrement. We first decrement, then push, decrement again, and then push. Let's see, register 3 and 4. That is from our our first two pop instructions. If you remember back in here, we push immediate 3 and 4 right after we push 1 and 2, and following our the stack characteristic LIFO characteristic. These are the first two that are popped from the stack, 4 and 3. Again, following LIFO, 5 and 6 are then popped from the stack. As you can see, visually comparing our memory contents with our registers 3 and 6, the orientation is maintained. Also here, we displayed at the top of the stack. This is to demonstrate that the stack pointer is correctly incremented in decrements.
Excellent.
So now we'll be going to the rest of our enhancements. So first, this is our add saturated instruction. Essentially the same instruction as the add instruction, except when RS and except when the result of the addition is greater than the maximum amount of a signed integer or less than the amount of a signed integer, then we will set it to that maximum or minimum. We do this using the overflow flag. As you see here, we check the overflow flag. If it overflows, then we'll assign it to the max value.
So that's a new ALU opcode, right?
Correct. So here's an example. We're adding 3 and 5 together. Here's 3 and here's 5. We add them together and we put it into 4.
I had a typo.
Sorry.
Yeah.
Please excuse the typo on this page. We'll further demonstrate we'll further explain the verification in our log file.
Yeah.
Next we have our subtraction saturated instruction. Again, same thing as the add, same concept, except now we're using the subtract operation.
So in other words, if you subtract and it would wrap around, you truncate to 0? Is that what you do? See, it says same thing, so I think we need an explanation. What does subtract saturated do?
So if the result is outside the range of a signed integer, it will just set it to that maximum or set it to that minimum.
So we're talking about a top level range, not the bottom level.
Both.
Give us an 8-bit example.
An 8-bit example. So if we have 7F, which is the maximum amount for 8-bit,
Right.
And we add it with 2, then it will,
Subtracting.
or then we subtracted with the
A -1, so that's what you're saying?
yeah.
Like an 8.
So it'll put it at 7F. Okay. So it doesn't have to do with the bottom, it has to do with the top.
It's implemented to do both. So you can see here, we have a if statement for, I guess, the top, the maximum
So if
amount.
we had a 0 - 1, you would truncate to 0.
No, it's signed, so it will go all the way to what the 8.
Okay, it's signed, okay, I'm thinking unsigned. So they have both, got it. Okay.
So here's our example. We have R17 subtracted by R20, and we have here is these are two very large negative numbers.
Right.
So when we subtract them, we'll get a the minimum amount for a signed integer. Our last enhancement is the absolute instruction. Very simple. It just I guess it changes the sign of a negative number to a positive number. And here's an example. R12 is, so we have R12 as our operand and R11 as our destination. And basically, this is -4 is in R12, and we will put into R11 +4. Oh, shoot. So here's our instruction memory module for to verify our saturated add, saturated subtract, and our absolute instruction. As you can see here, we have again just arbitrary load instructions. We're loading let's see 7FFF FFF8 into R1, 10 into R2, and 800000008 into R3. Our first instruction is add. So here's our log file. Again, R1, R2, and R3 are arbitrary values. We will add R1 and R2 into R4 because adding register 1 and register 2 will go over the maximum amount of assigned integer. The result is capped out at 7FFF FFFF. Similarly, for register 5, register 3 subtracted by register 2 will go under the minimum amount of assigned integer, and it will cap out at 800000000. Lastly, our absolute instruction is shown here. Again, it was our register 1 and register 3 that were used in our absolute instruction. Register 1, there's no change because it's already a positive number, and register 3 is a negative number and is converted into 7FFF FFF8.
So yeah, next we're going to feature enhancements. We first actually wanted to do vector arithmetic, and then floating point, and then baseline. The reason why we want to do it in that order is just because we wanted our processor to be more of an arithmetic processor. That's why we have absolute value, and also so then the vector arithmetic would help with the multiple SIMD unit, and then also floating points for decimals. So if anyone wanted to do any calculations with decimals, that'd be great. And then pipelining is for our throughput to make our processor more efficient. That's it. And then questions?
Good job.